All right, everyone, we are here. Finally, it is the day to learn an actual machine learning framework. The one that we're going to learn is called Pytorch, also known as Torch in just the Python module. It is absolutely incredible. I want you to know that it is finally the day of redemption. All of your strife learning this math is come to an end, because today we're going to leave behind all the math and see how we can get past it. Don't worry about it. Lock it away in some dark corner and move on with our human existences. So PyTorch is going to be your friend. It's going to be amazing. And the best thing is I'm going to explain how it helps your life with levels. So with levels of complexity. So with each level, I think and I hope you'll get a newfound sense of appreciation for just how amazing PyTorch is. So with that being said, we're going to be coding in Kaggle. If you want to follow along, you can sign up for a Kaggle account. Go to kaggle.com. You'll see a nice little link to create a Google account. And then once you've signed up, then you can go to kaggle.com. You'll land on the home page. You'll get a menu like this. Click create and create a new notebook. And you'll see something like this. You'll have a bunch of gobbledygook. Just delete that. I've introduced how to work with Kaggle before, but you can click on this left sidebar and press D twice and it will delete itself. And what I want you to do is import Numpy and Torch. And we're going to be comparing these two libraries just to see how these two modules they compare in terms of how helpful they are to us. Also, the way that I'm going to do this is I'm literally just going to repeat something we've already done, so you can see, in contrast, how much easier PyTorch is. And I'm going to work on the logistic regression problem we had earlier. If you want, I will take this link and put it in the description. And I know you can't see the button on the right, it says add data. But if you're working in Kaggle, just paste the link here and you'll find the dataset to add. And if you're not working in Kaggle, then you will be able to download the data to your local computer to work on it. So with that being said, take a second, pause the video if you want, and we're going to, after you're all done setting up, we're going to get started with figuring out how Kaggle works. So let's do it. Let's figure out, what is this amazing thing about PyTorch? What makes it so great? So the first thing that we can do with PyTorch is literally just use it as a substitute for NumPy. All the vector math that we could do earlier, we can do it now. So we're going to create, a little spark in our brain, to get started. Let's see. So before, the first thing I did was I just copied over all the code from our logistic regression lesson. So you can see we're loading up some data. We're, creating a sigmoid and a sigmoid prime, a derivative function, a feed forward function, and a cost function, and a gradient, backpropagation function, and finally a gradient descent function. So I'll just, load up all of these bits of code in NumPy, and you should see that they still work. Over here, and over here. And you can see, oh yeah, cost changing, code is working. So that is, the algorithm working in NumPy. But when I say, okay, we got to convert it to PyTorch, we can just substitute PyTorch for NumPy. It literally is that simple. First thing we got to do is we got to make sure that we convert from, remember, numpy.load, it creates a NumPy array. We got to convert from it to what is called a PyTorch tensor. So we use this Pytorch function called from numpy, and I'll show you what it creates. So I just passed in the numpy array, which I got from this np.load, and over here you can see it, outputs tensor and all of these numbers. The data type of the tensor is float64, which is just a very long decimal. So what this is saying is it's basically created this new type of variable. Now, keep in mind from our lesson on Python a few series ago, this new type of variable, it's basically just a class underneath the hood. It's just a class. So it's a predefined class. A tensor is a predefined class that Pytorch has created for us. So with that being said, it's that simple, how you can convert from the two. Notice that our data, I'll print out its shape. Oops, we have an error. Let's see if we can figure this out. So it says, okay, error is at this line over here. You can see with the arrow, and it says expected numpy array got its tensor. Well, the reason is because, we already converted x and set it to a tensor the first time. So when we're rerunning the code block, x is no longer a numpy array. So I'm just going to rerun this code block and then run this code block again. Now you see it gives us the size of the tensor. It's 4,238 examples by 5, input features. Keep in mind that this data, it's to predict, logistic regression problem, sorry, a binary classification problem with a logistic regression algorithm. And the problem is, will the patient get coronary heart disease sometime in the next 10 years? So that's the data we're working with. That's one part of converting from, let's say, NumPy code to Pytorch code. Make sure you're using Pytorch tensors, not NumPy arrays. And then the next part is kind of literally just, replace everything, you see as a NumPy with Torch. So here we went from numpy.exp, the exponent function, e to the whatever, to torch.exp, where it's still, doing the same thing. But it's not quite the same thing. It's almost the same thing. So I'll show you. Sometimes the libraries have a little bit of, a weird behavior. So let's say I do sigmoid 10 with np.exp, so numpy.exp, then, it's working. But if I do torch.exp, now it's going to give me a type error again. So it says the input. So when, we call the function here, this is called a stack trace, by the way. This line called this line over here, and it says that's where the error is. So what is the error specifically? It says the arguments, the inputs, must be a tensor, not an integer. So that's like a little bit of a, weird quirk. You gotta keep an eye out for these types of things. So torch.exp, it doesn't work on if you just, pass it a number. So what you might have to do is you create a torch.tensor. So torch.tensor, again, it's just a class that Pytorch has predefined for us, and it's creating a tensor out of this number. So now let's test it. You can see it's now working. So it created this tensor that was 10 long, and and gave us this output. It's again unit tests. It's really important to check different conditions. Let's do like a really bizarre tensor. So let's say random is equal to, in NumPy's case, we would do numpy.random.randn, and we could do like 5,000 by 1,000 by 10,000. So we could do like a weird 3-dimensional matrix here, and we could pass that in. But let's say we try it, with Torch, Pytorch, you can see we get an error. Module torch.random has no attribute random. What's saying is there's no function like this that we can just call. So what we got to do is we got to search for the docs. We got to figure out, how do we create a random number in Pytorch? We'll get these things called documentation. Basically, they just tell us, hey, here is the name of the function. This is what the function returns. And here are the parameters and optional parameters. These are the keyword arguments. These are the parameters and optional parameters that we can pass in. And most helpfully, it gives us an example. Thank God for the example. So you can see what you got to do is just call like torch.rand, torch.randn, and the dimensions. We can't go and just pass in an integer in the same way. So let's do that. Instead of torch.random.randn, we're going to do torch.justRandom. And now let's try it. It's taking a while to run. So as you can see here, maybe a 5,000 by 1,000 by 10,000 matrix. It's a bit too large, it looks like. So now we see like a limitation of our code that maybe it's not, great to run run with such large numbers. So hey, we learned something. And in Kaggle, when we try to use way too much memory, when we try to store such large things, then it's not going to work. So instead, what I'm going to do is just go 4,238 by 5, because our code will at least need to be able to handle that large of an input. So again, I'll need to restart my notebook. Let me close away this error. And I'll just rerun, these cells. There we are. Okay, this time it works. So it works for our purposes, but that is, the point of, testing use cases, unit tests, so that we can figure out, where does our algorithm work and not work. So anyways, these functions are working. We could, replace np.x with torch.x pretty easily. Let's try doing the same things here. So torch.dot and, torch.round instead of np.dot and np.round. Let's try testing this. So data, we can make it a random, random bunch of numbers. We're going to need to make it, 5 long, because that's the number of input features. We need 1 parameter per input feature. And now let's try running this. So feed forward, x data. Let's see what happens. Can we just, replace Numpy with the dot versions this time? Nope. All right, again, you see the stack trace. At feed forward, there was an error, and then at the very first line, torch.dot, there was an error. It says 1D tensors expected, but got 2D and 1D tensors. So it sounds like it's saying something about the dimensions, 2D and 1D. So let's print out the dimensions. So we can print x.shape, just like with NumPy we could do .shape. In Pytorch we can also do .shape. And data.shape, let's see, what are the 2 dimensions here. So the first dimension, it's 2-dimensional, 4,238 by 5. Second dimension is 1-dimensional, it's just 5. Okay, I see what it's saying, 2D and 1D tensors, but why can, np.dot not work? That should be defined. So now the second step is we got to search up the actual function. So why does this not work? So we look at the docs and see what happens. Okay, computes the dot product of 2 1D tensors. Oh, it literally says a note. And like NumPy's dots, this, only works with 2 1D tensors with the same number of elements. Oh, okay. So what do we do? If we wanna if we wanna do something that doesn't have, just one-dimensional tensors. Okay, so that's bizarre. Uh, ah, here we have a Stack Overflow thread. Stack Overflow is an amazing site. And it also tells us, some more information here. So here, someone's asking a question. They say that, they have the error. And then someone suggesting that we use this other function, torch.mm. We can use that. Okay, okay. And there's also this other thing, .matmul. All right, well, this is a bit complicated. Again, we can search up the docs. So let's search up torch.mm first. And, we'd continue to do that and, we'd go through that. So I'm going to spare you that process of, going through and figuring out the docs, though that's something you'll have to do a lot. What I know secretly is that we can use something else in Pytorch to do this. There's this operator. It's just called @ So just like the @ symbol, like in an email, that does the dot product that we want. It just so happens to be. So there you go. It'll save you, some debugging, but you'd have to do that a lot. Now, let's see. Does this work? Oh, we have another error. So it expected scalar type double, but found float. What does that mean? You remember how we printed X a while back and it said, float 64, and I was like, that's just a really long decimal. So in PyTorch, what's happening is, let me show you. So I can print x.dtype, the data type, and data.dtype. One is torch.float64, that's like a really long decimal. The other is float32, that's a shorter decimal. This is called a double, often in coding outside PyTorch. This is called a float. So what this is saying is because this first input was of type double, then it expected that data would also be type double. However, in PyTorch, the default is everything is a float. So what I'm going to do actually is I'm going to go up here and change these from doubles to floats. I don't care too much about accuracy right now, so that's an easy solution. Again, if I try to run this, it won't work because, we already set x to a tensor. So we got to run this first and run this. And now, these are still the same. Let's try this again. All right, so you can see now both of these are floats. I'm going to remove this print statement that we did for debugging. And now our code is working, yay. So again, some things, that you have to think about. What data type is it? Is the uh, is the method that I'm using, is it the exact same or there are a few differences? So a little bit more complex, don't worry, it gets better. So everything else is working. This torch.round function is working as expected. However, so one thing I did want to say, if you didn't see my note in another part of the series, we don't want to round this to 0 or 1, throughout the process where you're losing some precision. Because, later on we have a cost function where we use this prediction value that we get in order to compute what is the cost. So, we're losing precision. And there's going to be another fundamental issue later on in PyTorch, which I'll mention maybe later. But for now, just know, you know what, whatever. Yeah, like I get it. You're supposed to have it rounded, but we'll just round later on, okay? We'll be like, yeah, you know what? Just, give me the feed forward value. And then I'll round later on, when I need to present the data. And then we can round here outside the function. This is just because, we're going to keep a little bit more precision, we're going to be more accurate, and we're going to have an issue later on that we're going to prevent. So I'm just going to do that. Cost function, same thing, the only NP that we have to replace here is torch.sum. Let's see if this is working. So I need to pass in a prediction and a y value. So what I'm going to do is I'm going to use this feedforward function to get the prediction. Pred, I know it's not rounded, whatever, it's close enough. Pred is equal to feedforward. And then over here, I need to pass in x and data, which I already defined above. And then for the cost, I need to send in the prediction. And we need to send in y. Let's see if this works. Okay, yay, it's working. One issue that I'm noticing is it's just returning a tensor here. Tensor only has one number, the average per example, which is what we expect. However, if it is just one number, I just, like it to be a number. We're not using the costs later on. So what I could do is I could, round this. We'll leave it. We'll deal with it later on. However, if you did want, it to be converted to a number, you could convert it using some kind of Pytorch. Sorry, this is just a Python method. So for now, I'm going to leave it, especially because later on we might find it useful to have a tensor. But let's keep going. Finally, again, replace this and this. We already figured out, okay, wow, dot dot doesn't work for two-dimensional tensors. So I'm going to just already preemptively take out dot dot and use the at operator. Let's see if this gives us what we want. So for gradient vectorized, we need to pass in the prediction. So I'm just going to go feed forward. So pred is equal to feed forward x in data. And then we need to pass in an x and a y. So pred x, y. Does this work? Yay, it's working. All right. Yay, that's nice. It's nice when we don't get errors. So that code is working too. And it's nice. Oh, it recognizes the axis keyword argument too. So we could look up, how does torch.sum work? Again, look in the doc, see if they're actually similar. Last one, and then we'll be done. All right. Here, we don't have any more, NPs to replace with torches. So one here. Again, it's not torch.random.random. It's just random. So let's try this. Is this working? Ooh, that's a mess. Wow. All right, so what's going on here? Okay, I see. So when we have cost.history, that's the array that's keeping track, that's the list in Python that's keeping track of the cost over time. That's what we're printing here. And it's all tensors because, over here, we're appending tensors. Cost is a tensor. So over here now, I will then, convert the cost to a floating point number. The reason why it's better to do this here is because here it's not saving, it's not saving the cost that we get back as a floating point number. It's actually creating, a copy of that tensor, then converting it to a float and, sending it to this list, but it doesn't modify the cost afterwards, just in case we want to use it later. So I like this code more. Let's try this again, print it out. All right, you can see, it's changing. Ooh, doesn't look like it's, changing for the best. It looks like it's increasing over time, but hey, that's the first part. That is level 1 done. We have generated a tiny little brain, a start, the use of vector math with Pytorch. Right now, I know you're thinking though, hey, that just seems like inconvenient. Now I just have to worry about data types and sizes and, new functions I have to learn. What's the advantage here? I don't see that. All right, be patient, my friend. Let's move on to part 2. So level 2 is I hate backpropagation. I do not want to do whatever this bizarre, wacky thing is. Okay, I do not want to have to deal with this. So let me let you in on an amazing secret. The thing that's special about Pytorch and its tensors, you see these tensors? The thing that's special about these is Pytorch can automatically track everything, every calculation, every addition, subtraction, multiplication, everything you do with these tensors. And it's doing that in the background. And why is it doing it in the background? It's doing this because form it can form partial derivatives by itself. So when we had partial derivatives, we'd have different equations, right? So we might have z, that's not a great color, we might have z is equal to x, and then multiply by theta, dot product theta, and then we might have a is equal to the sigmoid of z. Well, Pytorch, if it gets, this tensor A, then it already kind of builds these equations in the storage. It keeps in mind, oh, how did I get this value A? Well, I got it from, this function, which took in, this input, which was generated by this equation. And at the end of the day, I want, partial, by theta, then I can go back across all of these layers and do that gradient, do that chain rule, that backpropagation myself. Now, in practical terms, what that means is you only ever need to code out the equations that, get the feed forward over here, and Pytorch can automatically do the backpropagation part for you. It'll figure it all out. Isn't that amazing? So let me show you. Let's expand our brain capacity a bit. Let's get those neurons firing. So what we're going to do is over here, we already, got these tensors earlier, so I'm going to leave this. Now what we're going to do is I'm going to create this new parameter, theta underscore with Pytorch. Again, it's gonna be created randomly with this function. However, what I'm going to do is I'm going to call this method of this tensor. Remember, torch.random, it's creating a tensor, and a tensor is just a class that has been predefined. Someone, predefined a method in that class that is require underscore grad underscore. By the way, just a Pytorch thing, whenever you have that underscore at the end of the function, it means it's modifying this value directly. Remember when I did the float cost and I was like, yeah, this is creating a copy. It's not modifying the value directly. So in this case, if we didn't have this, then we would have to save data with Pytorch because this is going to return a new value. In this case, we don't, because we're just saying, hey, go modify, this variable directly. So this requires grad function. That stands for requires gradient. We need a gradient generated for this theta parameter later on. So that's why we, call this and say, hey, Pytorch, please start tracking the calculations we do here. And we got to enable this setting because, otherwise it would take up a lot of memory, It doesn't want to track things more than is necessary. Pytorch doesn't like backpropagation either. So we're going to do this here. And now you see it's got a class and it has this new attribute, requires grad is equal to true. Before we just got, okay, here's a tensor. Now we have this new requires grad is equal to true. We have this new part of the tensor. So we're gonna define a gradient descent function, I'm going to show you the key parts. So, up here we had our gradient descent function. We basically have the same code, except we don't need, this is not the gradient descent part. This is the backpropagation part. Sorry. Sometimes I make errors too. So we don't need, this entire function that we have to define to calculate the backpropagation. What we could do is the first part is the same. So we're generating a prediction, then the cost, and data, it's tracking. Oh, it was used in this calculation, then this calculation. We're again appending the cost. I'm going to do floats again so that I don't have, tensors. Here are the key parts now. First key part, cost.backward. This is the backpropagation part. This is the function that we did not have to code, that Pytorch automatically created for us. Isn't that amazing? So we don't have to code anything. It already does backpropagation. Then what we have to do is we have to implement, this equation where we take data and run the gradient descent on it. So data minus the learning rate times the gradient. Now when we do that, remember data is a variable. In this case, data with Pytorch that we declared up here, it's a variable that we set to a tracking mode on. So when we're using this variable now, when we're adjusting it, we don't want the tracking mode to continue. So what we got to do is we got to use the special notation with torch dot no_grad. That means do not track any of these calculations in this coding block. Remember, Python, indentation is important. If I did this, it wouldn't work. So within this coding block, do not track any of the following calculations. And the key part that's happening here is over here. So just like before, you saw I had the gradient over here. The gradient was returned from a backpropagation function here. Here, with Pytorch, this is the backpropagation function. And it doesn't, return any values to us. What it does is it goes to the variable we have defined that says, hey, track gradients. And remember, that's just a class. So it creates an attribute in that class called grad. And this attribute, it will store the gradient that was returned. Just like this gradient variable, it stores, this gradient that we have returned here. Over here, that is stored in data.grad. So here is the key line of code, data minus equals the learning rate times data.grad. That means data is equal to, that's just a short form for data is equal to data minus learning rate times data.grad. So that just means the same thing. This is doing the gradient descent update now. Now I have this key line of code just to code a little bit more defensively, just to make sure there are no errors. Data.grad, sometimes it can mess up, things can go wrong. So what this is doing, remember data.grad has the backpropagation value. I'm just making sure that, it's not nan. So what I'm doing here is I have torch.isNan, data.grad any. So that'll return true if there's something wrong with the values. So it'll actually return, true and false for each element of the tensor. So, is the first value nan? Is the second value nan? Is the third value nan? And then .any, what it does is, this part returns a list that is true. This first value is nan, false. This second value isn't, and false. This third value isn't. And what .any does is it basically asks, are any of them true or false? Are any of them true? So in that list above, I showed you how one of the values, the first value was true, so that would return true. So this will return true if there's something wrong with the gradients. However, here's one mistake that I just realized. Oopsies, let's fix this. What we want is the opposite of this. So before it was going to run, it was going to return true if any of the gradients were abnormal, if they were nan, not a number. And then only if there was a mistake, then it would run this line of code. We don't want that. We want the opposite. So I put a not here. So this will return true if there's any mistakes. But if there's not any mistakes, if there's not any mistakes, then go run the gradient descent update. Take a second, pause if you need, review that. I know that I said that's a bit fast. It's fine, take a second, pause if you need. So I hope you understand these 4 lines. This is the key part. No matter how complicated our functions, we don't have to code the backpropagation anymore. This is just, a complexity that'll soon go away with another level. This is just a tiny detail that I'm just putting in just to make sure nothing's wrong. And over here is like the big gradient descent part, same as above. Finally, one last thing we have to do is we gotta set the gradients back to 0. What happens is this .grad variable, again, remember this is an attribute. It was set to something, it was set to a number. If we don't set it back to 0 at the end, for the next iteration, what Pytorch is going to do is it's going to keep adding to that attribute. So the attribute might be like 2.5, and now it adds, the next time that we run this loop, it might add, another 2.5 on top. So what we got to do is just use this 0, again, 0 underscore. It just means it's called in place. It directly modifies data.grad instead of us needing to save, data.grad is equal to some function like this. So we just use this so that we can reset the gradient calculation so that Pytorch can again make our life simple the next time we run this loop. So here we are, that's the gradient descent function done. Again, take a second, pause if you need, review the code. But this is the key part, the key new part that Pytorch is doing for us. And again, I'm going to test it out here. Let's see, is it working? Yep, we're getting back a cost. Yay! We should be getting back a cost. Then we can do cost.backwards. And, I just wanted to show you here. After we run cost.backward, then you can see that a gradient has been set. So in this case, the gradients are all 0. There's not much to adjust. I'm going to delete these here. We don't need those anymore. So again, reset the variables. Cool. Here's the function defined, and I'm going to try running the function. So just set a few parameters here. Let's see how this runs. We have some kind of error here. So you can see the cost is always the same across all iterations. It seems like something is not working. Let's just make sure that this step is working. So, if this actually works, I'm gonna, because I wasn't sure about this logic, I made a mistake here. Let's just print an X and then, end is equal to nothing. Don't start a new line. So if this actual step is happening, that's good to check. Let's try again. All right, it's working. However, it's not working. Oh well. So for now, what we see is that this basic logic, hopefully it makes sense. This piece of code about propagation, this piece of code, make sure you're not tracking any more changes while we run the gradient descent updates. So that's a key part of being able to run this, gradient descent a lot more easily. And if you want, I'll link another resource that explains, how does Pytorch do this? How does it automatically do this behind the scenes? Now, with that being said, I do want to go on to the next level now, where we're gonna simplify this even further. So again, expanding our brain. Let's get some connections going. Let's use some magical libraries in Pytorch called torch.nn for neural network and torch.nn.functional to be able to have some more variety in our algorithm. So right now, let's say, we didn't like, I think I mentioned, the cost function here. This is a mean squared error cost function. In another video, I mentioned how mean squared error isn't the best cost function to use when it comes to logistic regression. But I don't want to go code out, another cost function by hand. If I want to change something, I just want to change it. So what if Pytorch could give us some flexibility? Well, as you might expect, torch.nn.functional, it has functions. Specifically, here, I can just do torch.nn.functional and then a function name. So if I click on this link, again, you can go search up the docs for this module, and you'll see there are so many functions here. We have convolution functions. Those are for convolutional neural networks. We might have activation functions. We might have, hey, our old friend ReLU, you know ReLU, a bunch of complicated ones that even I don't know, and maybe you want to search some of these up. But you can see just how many functions there are. So if anything, you might get lost. That's how many functions there are, but there is certainly, everything you need and more. So I'm going to scroll down to loss functions. That's how I found out, which ones I had available. And torch.nn.functional, basically, that's a function. I'm going to set it to a simpler variable for me to reference data. Same thing for these activation functions. So here are two loss functions, two activation functions. This linear function, it's what it does is it does, that z is equal to x at data thing, the dot product. And instead of, z and x and data, it's just y is equal to a times, b, some matrices. So it's just a general implementation of that. So now look at my feed forward function. It's so much more simple. Before, if you saw my feed forward function, I'd have to worry about math and I have to code the equations by hand. Now, what I can do is I can just go return, linear x and theta. That does the, as I mentioned, x at theta thing, the dot product. Then I pass that through a sigmoid function and I just return that. Cool. And the cost, I just pass it through this function. Remember, I'm just setting like these variables as references to the function names. And let's see, we have an error. Linear is not defined. Hey, but I defined it here. Here we are. And here it gives us a warning. So it says nn.functional.sigmoid is deprecated. Use torch.sigmoid instead. So let me just change up the code here. So instead of nn.functional.sigmoid, I'll do what it says, torch.sigmoid. Cool. Isn't that great? And now look, if I wanted to change up some of my functions, I can just put in ReLU here instead of, say, sigmoid, if I so wanted. And here I'll do cross entropy loss instead of binary cross entropy. Okay, I will not do cross entropy loss. That one does not work because I think I'm passing in the wrong inputs. And we could go search up the docs for cross entropy loss to see what this specific error is. And BC will not work because, we did a ReLU. Okay, why don't we try mean squared error loss? So just to show you that ReLU could work, let's see. Do we have mean squared error loss? MSE underscore loss. So let's create mean squared error. Where is it? MSE is equal to torch.nn.functional mean squared error. There we are. Figuring things out as we go. So let's run this again. No. MSC loss. Oops, no, it's MSC error. I have the memory of a goldfish. All right, there we are. So this case it works, but we're not gonna do that because we need logistic regression to happen. So hopefully now you can see, with all of these varieties, you can just switch up the cost functions and the loss functions whenever you want, and you don't have to code a thing. Hopefully you like that aspect of Pytorch. Let's move on to another level. So now we're gonna, really have the neurons take off. So one thing that we've had to do so far is like we've had to, keep track of all these random variables. We've had, these predictions and cost values. We had the data with Pytorch parameters, and we have to like set the gradients and stuff. That's not so great. I don't like that. So what we're gonna do is we're gonna use some classes in Pytorch that are built to store the common tools of neural networks, specifically common tools being the parameters, the layers, the functions like get cost, things like that. And the first thing that I want you to know is these are all just classes at the end of the day. So these are just classes that someone has created for us, and we can use in order to use their functionalities. So the first thing we're going to do is we're going to use torch.nn.module, capital M. It's going to be, by the way, when you have capital after nn, here you see you have these lower cases with functional. So that kind of means, this is a function. With the capitals, that means these are classes. So these are predefined functions, these are predefined classes. So this class will store, all of the code basically, including this class called torch.nn.parameter, which stores specifically parameter values. So let's take a look at how this works. So it looks like a little bit less abstract. So to use these classes, keep in mind, these are PyTorch classes. So to use them, we have to work with classes. We can't just use functions like we were doing before. So let me show you the code here. The first thing that we're going to do is we want to actually use this torch.nn.module class. Now this is a predefined class. In fact, if you want, you can search up torch.nn.module and source code, and you will literally see, here is the exact code that is in that class. You can do this for any PyTorch class. So this is taking a little while to load, but you can see, a bunch of complicated code that you don't need to understand because PyTorch, took care of it for you. So this is like what we're doing. We're literally creating class that imports in code from elsewhere. And to get that code, we're creating a child class. My model, it extends off of torch.nn module, which means it just uses that code from that class and pulls it over. The way it does that, again, if you're unfamiliar with classes, go back to the second Python tutorial a few videos back. But calling super goes to this class, and then initializing that class, it just means, hey, take that code from over there and bring it to, this class, this child class that I'm creating. So that's the first thing. That's how we use the torch.nn.module class. And this lets us do, a lot of fancy things, which you'll get to see soon. But then to initialize the second class, torch.nn parameter, to store, the parameters, then what we do is we say self.data, that's like creating an attribute of this child class. And then we do torch.nn.parameter, and we pass in, the values we'd like to store as a parameter. So pretty intuitive, but you might be wondering, well, why don't we just, do it like we did earlier, just set data to torch.random5, 5 random values. Why do we have this parameter business? Well, it's doing a few useful things behind the scenes. The first useful thing it's doing, we don't have to set, this requires gradients anymore. It'll already take care of that. The next useful thing that it does, you'll see when we get to the gradient descent parts, but let's say we're doing forward. So we have to create a forward function to be able to use torch.nn.module. And this is, keep in mind, this is a reserved name in Pytorch. So what that means is Pytorch, it doesn't, define a feed forward function. It has a forward function. And when we create this, technically method, it should be called, when we create this method of a child class of torch.nn.module, what this is going to do is it's going to, store it away so that I can use it as soon as it needs it. So it's going to do special things with it, but we're just doing the same thing as before. We had a sigmoid function defined earlier and a linear function. Instead of data, we use self.data because, we initialized it earlier. But now, same thing with the cost, we just use that function that we defined earlier over here, binary cross entropy, and it'll take care of everything for us. However, key thing to keep in mind is now, look, so this is, the template, this is the class, this is the instance of the child class, right? It's an instance of my model. Look, I can just, call that instance. I can just send in some data, and behind the scenes, what Pytorch does is it automatically calls this forward function. This may sound like, oh, it's just a small convenience, I just have to, it saves me the trouble of writing, dot forward. It just seems like a tiny convenience. However, it gets a lot more convenient than that, as you'll see later, because we can actually, pass this class and many other classes to Pytorch of different models we have. We can stack them together, we can, package in different layers, and it'll automatically run through all of these classes. You'll get to hear more about that idea later in the next lesson about neural networks. So this is just how we use, torch.nn.module and torch.nn.parameter. The advantage of torch.nn.module is that we can access a lot of code that Pytorch has already written for us. For example, the automatic forwarding of the classes. Another thing is, this is the key thing, which you'll see when we do the gradient descent. How another benefit here, as you can see, okay, first product gradient descent is just the same. So, get the prediction, get the cost, save the cost. But now this time, this is, running the back propagation. Now, hey, don't track any more, gradient calculations. Now look, so in the child instance we created, so, this instance of the child class, because we had used some code from torch.nn.module, what it did was it saved all of the parameters that we declared with torch.nn.parameter. It saved all of them in, this class and under some attributes which we get back when we call this method .parameters. Now in this case we only have one parameter, self.data, but if you think about what will happen with neural networks, well, we will have like, data 1, data 2, data 3, and so on and so on and so on. as we go through the different layers of the neural networks. And we don't just have datas. Remember, if you think back to the notation earlier, we'll have weights and biases across tens of layers, hundreds of layers. So this is like a huge improvement over being able to, just say, oh yeah, one at a time, I'll go through, data one, data two, data three, and so on and so on. So that's cool. That's nice, especially when we get to neural networks. And you can see over here, we have this dot zero underscore grad method. It just, goes through all of the parameters and zeroes out their gradients. So that is the advantage of torch.nn.module and torch.nn.parameter. It automatically stores all of the parameters and it lets us work with them at the same time. So over here, cost history, you see that bit of code worked, all of that is working. Now, there is one last level, and then basically we were done. The last level is just, hey, Pytorch, could you just take care of everything for me? And what we'll do is we're going to use torch.nn.layerName. So just like we had torch.nn.functional.sigmoid.relu.linear, we're going to just use, layer names with a capital this time. So I'll show you below what the difference is, but we're going to use these layer names as classes that have their own, they create their own parameters. We don't need to initialize, datas or anything. And then we'll use torch.nn.sequential to basically order all of these layers. So what's going on behind the scenes is it's creating, these child classes of torch.nn.module for us. So I'll show you what I mean in just a sec. Now, here you can see our brain is really expanding. It's reaching full consciousness. Here, I'll show you some code. So I've just quickly defined some dimensions of, what are the X features that are going in to our logistic regression, and then what are the dimensions of the activation that we're getting out. So you can see here, what I did is I created torch.nn.sequential. That is a class that stores, all of these layer classes that create their own parameters. The way that I can create this class is I'll just have torch.nn.sequential, and then, in the parentheses as its arguments, I just pass in as many classes as I want. So I can pass in a torch.nn.linear class. This is a predefined class in Pytorch. You can, again, search up the source code. And it takes in, 5 input features and, multiple examples of those. And then it returns, a one-dimensional output. So that's kind of like the way that it knows which parameters do I need to create here. Like we don't need to tell it, hey, you need 5 data parameters. It knows, okay, I need to do a linear operation. That just means, I need to do that dot product thing. And I need to go from a 5-dimensional input to a 1-dimensional output. Again, multiple examples. So it'll automatically know, hey, go create a data parameter that has those dimensions. After that, we have a torch.nn.sigmoid. That is kind of the equivalent to this function that we were calling, but this time it's a class. So again, this time it is this code right here. It is a class, just like here, that is a child class of torch.nn.module instead of a function. That's what the difference is between torch.nn.layerName and torch.nn.functional layerName. these functional layer names, these are functions that we can call. These things over here, these are classes. The reason why the classes are nice is because we can stack them together and we can use them with other Pytorch classes. Notice that here we don't have, a dot functional, and also we don't have a lowercase name. So that in Pytorch is the difference for these classes, these predefined classes. For these predefined classes, we're going to have an uppercase name. So now, look how simple our code is. So let's see, we have an error. Let's fix the error after. But this is like us defining the model. So remember, this is like creating a class for us. So it's just like, when we created this child instance is equal to my model, except this time we don't have to define what my model is. PyTorch does it for us, isn't that great? And it already created the parameters, so very easy. Now, once we created that, again, we're doing the exact same thing as before. However, keep in mind, because we're using, predefined PyTorch classes, then PyTorch has certain expectations. You can search up the documentation for these classes to figure out, what is going wrong. So here, what it's saying is, one, it's pointing to this line. So torch.nn.functional binary cross entropy. So this line is where there is an error. It says using a target size, input size. Oh, that seems like there is something wrong with the sizes of these two things. So let's print out. By size, it just means shape, by the way. So you want to print out, the shape here of prediction and the shape here of y. Let's see what the issue is. So one of these is a two-dimensional matrix, kinda, not really. It's just like 4,238 by 1, but in PyTorch land behind the scenes, it's treating it as two-dimensional. And then over here, this is just 4,238. Now it seems like a small difference. They're really the same values. PyTorch just stored them a bit differently behind the scenes. So how can we fix that? What we're going to use is a function that is called .squeeze. Yes. There we are. What the squeeze function does is, you can think, over here we have these two dimensions where we really just need one. Really, we just need, okay, 4,238, and just that is it. We don't need a column dimension. So what it's going to try and do is it's going to squeeze this column dimension into just, one smaller dimensional matrix. I know that sounds weird. So let me actually, before I run this here, let me show you what happens so that just so you can see. So what I do is I put in squeeze, and I need to specify, which dimension do I squeeze. So I'm going to pick, this last dimension. So I'm going to put in -1. Let's see what happens when I run the code this time. So you can see here now, instead of 4,238 by 1, I just have 4,238. That's why I put the -1. Otherwise it wouldn't work. If I run this, you can see it doesn't work. This time it does work. Well, I'm wrong. Oops. Well, maybe sometimes you don't need to put in the squeeze dimension. However, it's just a nice practice. So you can see now we have the 1. Now we don't have the 1. So what I'm going to do here is, because now it seems like, there's not going to be an issue. The sizes are the same. I can see both sizes are the same. I'll put in .squeeze here, and let's see what happens. All right, so it's working, yay. So a few hassles in, using different classes that we haven't defined, but it's a lot more simple. We don't have to even create our own classes, so I'm liking this, especially if we have to create lots of layers. So in a neural network, the next lesson you'll see how we extend this, how we can create lots of different layers in, sequential. By the way, sequential just means Pytorch. Remember what I said? It's this is a special method name, and it automatically calls these behind the scene. Well, that's what sequential is doing. It just takes in the arguments that we passed in order, and then it calls the forward method of all of these different classes. In fact, we could even put in our custom class right here. So our custom class is called my_model. We could put it in over here. And Pytorch would know, hey, just call the forward method. That's why we have to make sure that we have a forward method here. So that's why, you have to be a little bit careful. But if you follow Pytorch's rules, if you play nice, then Pytorch will be very nice to you. It will let you, do a lot of fancy, complicated things in whatever order you want. In this case, this might not work just because the input dimensions here and here, they wouldn't align. More specifically, output here wouldn't align with the inputs here, but in general, you could create your own classes to use here if you use torch.nn.module. Hopefully, that's cool. Now, again, we're trying to get it to do everything for us in this last level of convenience. So never mind the whole gradient descent thing. We're going to use a library called torch.optim for optimization to take care of, the optimization algorithm parts. So here's our new gradient descent function. What we have to do is we have to create an optimizer using torch.optim. If you search this up, this library, you'll see a bunch of very different options, but the one that I'm going to use is stochastic gradient descent. If you go back a few lessons to alternative optimization algorithms, you can find that. And we can use this, we can use Atom, we can use RMS prop. There are so many we can use, all by just changing whichever class we call. So here, predefined class, we call it. We have to put in the model.parameters. We got it from torch.nn.sequential because again, it is still just using torch.nn.module, which auto creates those parameters. When these layers, these layers make their own parameters, this grabs the parameters, torch.nn.sequential from its layers, and torch.nn.module then, packages them up nice for us here. We pass in a learning rate, and now we've created our optimizer. So you can see here, pretty simple. We just read the prediction as we did. We get the cost as we did. And we're gonna have to squeeze this as we did. And that first part is, pretty simple. It's pretty nice. But now, hey, we can just, call back propagation in one line, opt.step. What this does is it runs this step calculation, take a step closer towards the minimum. And also opt.zeroGrad, it just goes through all of these parameters and it goes and sets their gradient to 0 again for the next iteration. So I'm going to run this, and hopefully you can see that it's so much simpler than it ran. Sorry, sometimes the Kaggle loop gets spinning forever, but hopefully you can see how much simpler this is compared to the mess that we started with. All of these different lines of code. So that is basically how Pytorch, organizes basically everything when running a neural network. By the way, there's so much more behind the scenes. So for example, there's so much helpful, there's so many helpful tools for pre-processing data. There's these libraries, torch.utils.data, torch vision, transforms, torch text, .data.utils. As you can imagine, this has to do with computer vision stuff, which we won't go into, and natural language processing stuff, which we also won't go into. We also can get data, data sets right from Pytorch. So common data sets, if you've ever heard of MNIST, MNIST, that's a very common one. So we can get, computer vision data sets, audio data sets, NLP textual data sets. So this is like really, full end-to-end superpowers right here. I'll just show you a quick example. So from torch.utils.data, it's literally just one library out of the many. I'm going to create a data set using this tensor dataset class and a data loader using this data set. What the data loader does is it basically chunks up the data given the batch size that we created. So this is like a really easy way to do batch gradient descent. Again, here I'm going to create, mini batch gradient descent. So we have the optimizer over here, defined just as we did earlier. But now look, so we have, a number of epochs. An epoch is basically how many times you run over your data set. You have this simple line to be able to like go through different batches, mini batches in our data sets for X and Y in loader. We can get the prediction for that X and the cost given that prediction in Y, and then, same as before. Now, if you created your own batch sizes, it would be so much more messy. You would have to like index in your data and select the right rows. Like this is so much more easy. So I just wanted to show you that there is like this entire world of difference. Let's see, we did another error. That's cool. Let's see if we can figure it out. Again, the sizes are different. So we gotta put in, I think, pred.squeeze. That is correct. At -1. Cool. So this time it's running. Yay. So again, this is just like an intro to Pytorch and all of that data stuff, just so you know, hey, there's so much more out there. There is so much more that you could learn about with Pytorch to really, just become cosmically superpowered. You can, I'll leave a link to this notebook in the description and the data set that I was working with in the description. You can click on these links that I've left to basically the introduction to Pytorch. Pytorch has so many amazing tutorials on its websites. I really recommend, this what is torch.nn really, a behind the scenes tutorial. And here, there's like a full on every single concept that you could want to learn in Pytorch. So highly recommend these things. That being said, we are now done for today. In the next lesson, we're going to use Pytorch to create a neural network very, very simply.